Okay, so hello and welcome everyone to week 12 of interactive live sessions for the course on fundamentals of convective heat transfer. So this course is being offered by NPTEL, being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I am the TA for this course, and like the entire course duration, today also we will solve some problems together. Now, uh, this is the last week as such. So this was a 12-week course, and for every week we had 3 or 4 lectures and then one tutorial session. So this is the 12th tutorial session for the 12th week. And after this, next week also we will have one session in which we will cover the entire course to have a final revision before going into the exam. So without further ado, let's get started. We'll get started with today's first problem, which is asking us that in the pool boiling curve, the point after the onset of nucleate boiling, where the heat transfer rate is minimum, is known as what? Is it option A, the inflection point, option B, the Leidenfrost point, or option C, the critical point? Or is it option D, there is none of the above is true? Okay, we have one quick response in the chat box saying that it should be option B, the Leidenfrost point. So if we have a look at the solution, it is indeed the Leidenfrost point. So you had done that correctly. So if we look at a typical pool boiling curve where this is delta T, the excess temperature, and we have the heat flux rate on the y-axis. So we have something like this. It slowly begins, reaches a maximum at the critical, then a minimum at the Leidenfrost point, and then keeps on increasing. So this here is the critical point, and this point over here is the Leidenfrost point. The onset of pool boiling is somewhere over here, which is known as ONB. So after this, the minimum point is this one, the Leidenfrost point. Okay, so that's why option B would be the correct answer, as you pointed out correctly. So that is what it is about this one. Any questions on this? Any questions on pool boiling curve?
No, sir.
Okay, then let's move along. We will move along to uh, question 2, which is asking us to. Okay, why is it blurry? Plus fine. Yeah. That's better. I hope. Mhm. Stop. I'll reshare my screen once again. Okay. So we are now at question 2, which has given us 6 different stages of flow boiling. We have to arrange them in the subsequent order of heating. So if as the temperature, the excess temperature increases, how will the different stages of flow boiling appear? You have to arrange them in the correct order. There are 6 different stages given here. We're looking for the correct order of that. So the different stages given are A. Slug flow, B. Mist flow, C. Annular flow, D. Bubbly flow, E. Single phase liquid flow, and option F. Single phase vapor flow. So we have one response in the chat box telling it should be E, D, A, C, B, F. So option E is single phase liquid flow and option F is single phase vapor flow. These are the two extreme ends. That's why E should be the first one and F should be the last one. Now, in between, from single phase vapor flow, little bubbles start appearing that we call as the bubbly flow. So E should give rise to D. Then after bubbly flow, so if I draw the figure here, so let's say this is increasing in temperature. So initially we have a liquid, single phase liquid flow, which we will call as E, and then later on we have vapor over here that we will call as F. Now in between, so after E, little bubbles start appearing. We call that as bubbly flow. So that is D. Then those bubbles, they grow bigger and coalesce with each other, forming bigger slugs of vapor. So that thing is known as slug flow. So D would give rise to A. Then after slug flow, this entire annulus gets filled with vapor and there is only a thin layer of liquid uh, near the wall. So this is known as annular flow, which is option C. And then after that, the there are it's majorly vapor with liquid, with small droplets of liquid in between, uh, floating around in between. That is known as the mist flow, which is option B. And after those liquid particles get evaporated as well, we will get pure vapor, and that is known as single phase vapor flow, which is option F. So this order should be the correct one. We will have a look at the solution, and indeed it is the correct one. Okay. So I hope there are no questions regarding this. If you have, please don't hesitate to ask. All right. So we will keep moving. Move on to question number 3 now, which is in this case you have to arrange the stages of pool boiling in the same increasing order of excess temperature. It's a similar question with some different stages now. Here we have option A, film boiling, option C, natural convection boiling, option C, nucleate boiling with bubbles reaching the surface, and option D, nucleate boiling with bubbles collapsing before reaching the surface. Before reaching the surface. And option E, transitional boiling. So one response in the chat box is B, D, C, E, A. B, D, C, E, A. Let's have a look at the correct solution. It is indeed B, D, C, E, A. You're correct. So for the pool boiling case, when the excess temperature is pretty less, we get natural convection boiling, that is option B, in which, let's say, if this is the heating surface, then this heated up the liquid, this heats up the liquid uh, just near to it, that gets lighter and goes up due to forces of buoyancy, and colder fluids from the top comes down. This sets up natural currents, and this is known as natural convection boiling. So option B would be the first case. Then this moves on to nucleate boiling, in which bubbles, little bubbles, they start appearing, but those bubbles cannot reach the free surface on top, because as this bubble goes up, the liquid around it is cooler than the saturation temperature. So so if I have a bubble going up like this, its ambient fluid is at a lower temperature than the saturation temperature. So what happens is that again condenses the vapor within the bubble, which becomes liquid again. So as this bubble goes up, it becomes smaller and smaller in diameter. So if I draw this correctly, so there will be a bubble formed like this, which will get smaller and smaller until it just disappears before reaching the surface. So we have, after option B, we will have option D, that is nucleate boiling, but with bubbles collapsing before reaching the surface. Then after this, we will get even bigger droplets, and as well as droplets which can, the rate of uh, creation of these droplets would also increase, which will reduce their frequency of collapsing, and as a result there will be surviving droplets which reach the free surface, where it will then evaporate upwards. So then after B, we will get uh, option C, that is nucleate boiling with bubbles reaching the free surface. Then after this, we will get option E, that is transitional boiling. In transitional boiling, what happens is that, so this is basically an in-between case between nucleate boiling and film boiling, which is the uh, final case. So in film boiling, there is a continuous film of vapor uh, below the liquid surface. So this is option E, option A, that is film boiling. And in between, there is a transitional case where there are films formed, there are nucleate boiling also goes on, and these films are not continuous. There is gaps between the films. So that this situation is known as transitional boiling, that is option E. So the correct order would be B, D, C, E, A. Okay. Any questions on this?
No, sir.
Okay. So we will keep moving. We'll move on to question number 4 now, which is asking for us to find the uh, convective coefficient for condensation usually lie in which range? Is it option A, 30 to 300 watt per meter square Kelvin? Is it 50 to 2000 watt per meter square Kelvin? Is it option C, 200 to 10,000 watt per meter square Kelvin? Or is it option D, 5,000 to 100,000 or 1 lakh watt per meter square Kelvin? What is the usual range for condensation heat transfer? So we have one response in favor of option D. Let's have a look at the solution, and it is indeed correct. So any phase change process means the convective coefficient will be very high. And this particular property is what is very useful in many engineering applications, and that is why learning phase change heat transfer is so important. So for case of condensation as well as boiling, the H could very well reach somewhere around 100,000 watt per meter square Kelvin. Now, this is not possible with natural convection or forced convection so easily. But phase change allows us to achieve these very high rates of convective heat transfer. Okay, so we will now move on to question number 5, which is asking us that dropwise condensation usually occurs on what? Oily surface, glazed surface, a smooth surface, or a coated surface? Where is the highest probability of getting dropwise condensation? So first of all, what is dropwise condensation? If we have a wall which is cooler than the ambient fluid around it, then that ambient fluid will condense on it. So another alternative of dropwise condensation is film condensation, in which a entire film, a continuous film of liquid is formed, and that goes down due to gravity like this. And the other option is it can condense in a dropwise manner, in which liquid drops would form like this, and these drops would now roll down due to gravity. Uh, so we have a few responses in the chat box telling us that it could be either C or B, a smooth surface or a coated surface. So let's have a look at the solution. It is actually a coated surface. So if a surface becomes coated with Teflon or other polymer like that, that really enhances dropwise condensation. So one of the main importances of dropwise condensation is that it has a higher convective, so HD being dropwise condensation rate, and let's say HF being the film condensation heat transfer rate. So in case of dropwise condensation, this heat transfer coefficient would be much higher. And the physical reason for that is if we have drops forming like this, then there is still this bare surface area of the cool solid which is still in contact with the ambient fluid. So more heat transfer can take place through there. Whereas in case of film condensation, there will be a film forming in between the cold surface and the ambient fluid, creating some resistance to the heat transfer between them. So this bare heat surface area is higher in this case, leading to a higher H. So that's why in many engineering applications where condensation is important, a coated surface is used to make sure that the condensation takes place in a dropwise manner and the heat transfer coefficient is high enough. Okay. Any questions on this?
Sir, I do have one question.
Yeah.
If we compare the heat transfer coefficient for boiling and condensation,
Hmm.
so normally in the condensation, the heat transfer coefficient is higher as compared to the boiling.
Yeah.
So is there any specific reason for this one?
So in case of condensation, the the vapor becomes liquid, right? So this is for condensation, and for boiling, a liquid turns into a vapor. Now, in general, the heat transfer rate for liquids is higher as compared to a vapor. Now, with condensation, more and more liquid is formed, so that really enhances the heat transfer rate. Whereas for boiling, more and more vapor is formed, and that reduces the heat transfer rate as compared to a pure liquid being in contact with solid. So with more condensation, more liquid and more heat transfer, and in case of boiling, with more boiling, more vapor, which sort of reduces the heat transfer rate, which we see in the pool boiling curve, right? So that's why uh, for similar excess temperatures, for comparable excess temperatures between the two, condensation heat transfer rate is usually a bit more than boiling. Situations are more complicated than that, but in general, this is the physics behind it. Does that make sense?
Yes, sir.
Okay.
Thank you.
Okay. Anything else? Okay. So we will move along. We'll move along to question number 6 now, which is telling us that from Nusselt analysis of laminar film condensation, this is a whole mathematical framework which we went through. The film thickness delta varies as x to the power n. So what is the value of n? That is the question. So for some context, this is a cold surface. Film condensation takes place on this, and as a result, this is the layer of liquid which flows down. Now, this is my y, this is my x, and this is the film thickness delta. Now I'm telling that this delta is proportional to x to the power n. What is the value of n as achieved from Nusselt analysis of that laminar film condensation? Is it option A 1 by 4, option B minus 1 by 4, option C 1 by 3, or is it option D 3 by 4? Yeah, we have a quick response in favor of option A. Let's see if we can get any more responses. No? Okay, so let's have a look at the solution. It is indeed option A, that is 1 by 4. So delta goes as x to the power 1 by 4 for laminar film condensation. The mathematical proof of this was discussed in the lecture. So if you have any questions on this, I'll suggest you to go back and look at it. Okay, we'll move along. We'll move along to question number 7 now, which is a true and false type of question, which is asking us that the statement is the nucleate boiling is not influenced by surface characteristics of the solid. Is that statement true or is it false? So if I have nucleate boiling going on like this, will the surface characteristics of this solid surface matter or not? Or to be more precise, does that influence nucleate boiling or not? So we have one response telling that it's false, option B. Let's see if there are more responses. Okay, let's have a look at the solution, and it is indeed false. The nucleate boiling is actually influenced by surface characteristics. So we have seen that for scored surfaces, the nucleate boiling is actually higher than for smooth surfaces. That's because if it's a rough surface in a microscopic level, so these points, they would allow more heat transfer between the solid surface and the liquid, and that would enhance nucleate boiling even more. So nucleate boiling is actually influenced. So telling that it's not influenced is false. Okay. Any questions on this?
Yes, sir.
Yeah,
Uh,
yeah, please
in
go ahead.
the calculation of that heat transfer coefficient
Hmm.
or the heat transfer rate,
Hmm.
one of the parameter was there the CSF, the
Yeah,
constant that decides
yeah,
on the surface and fluid characteristics.
yeah.
So that could be also one of the justification for this question.
Yeah, justification as in this CSF captures the effect of being a scored or a smooth surface. So this CSF comes from experiments, right? Now the physical reason for that is this, that due to more roughness, the local surface area increases and that enhances the heat transfer. And how to capture that mathematically, CSF comes into play over there. It's not that because of CSF these things are happening. These things are happening due to physical reasons. CSF is just capturing that effect mathematically.
Okay, sir. Yes.
Okay. Yeah. So we'll move on to the last question of today's session now, which is asking us that for a Reynolds number in the range of 30 to 1800, the flow regime in film condensation over a vertical plate is what? Is it option A, wave free flow, option B, turbulent flow, option C, wavy laminar flow, or option D, stratified flow? So this is in regards to film condensation once again. And the Reynolds number over here is with respect to delta. So Reynolds number being uh, U delta by over nu. So if Reynolds number is between 30 to 1800, is it wave free flow? Is it turbulent flow? Is it wavy laminar flow? Or is it option D, stratified flow? We have one response in the chat box telling it should be wavy laminar flow. Let's see if we get any more responses. So what happens is with increasing x, the Reynolds number also increases as delta increases, and u is a function of delta, and that also increases with increasing x. Now that results in Reynolds number also increasing. So up to a certain region, it remains laminar. So, and this is up to a Reynolds number of 30, and beyond a certain Reynolds number of 1800, it becomes turbulent. Now in between, there is a transitional zone from laminar to turbulent, which is known as the wavy laminar flow. So in between this, there will be perfectly parallel lines of laminar flow. Then these lines would start showing some waves like this. But the general properties of laminar flow is still uh, conserved within this. Then after 1800, this chaotic motion sets in. We start getting eddies and energy cascade and everything that is associated with turbulent flow over here. So this becomes fully turbulent. The region in between, we get wavy lamina. So option C is the correct answer. Any questions on this? No? Okay, so this was the last question for today's session. Thank you all for joining and participating. We will meet for the last time next week when we will discuss. Maybe I'll try to set one question from every week, and or broadly every topic that we have covered, and you can come with all of your doubts that you may have regarding anything. Okay.
Sure, sir.
Okay. So thank you. See you next week. Bye.
Thank you, sir.